Next, we're going to look at a numerical summary measure that allows us to evaluate how good a regression model is doing with respect to predicting estimating y. This numerical summary measure is called the coefficient of determination, although most people just simply call it R squared for short. Okay, so to help set this up, let's suppose that we didn't actually have an independent variable or explanatory variable to estimate y. And so that essentially, if we wanted to estimate y, all we had available to us essentially was the sample mean. So how good will the sample mean then do in predicting what all the y's are? And as you might expect, it probably wouldn't do a very good job. So what we're going to do as a measure of how good it does, we're going to take the sum of all of our observed y's minus the corresponding predicted y that we would get, and we square that before we do the corresponding summation. So in other words, we're going to take y sub I minus y bar, square it, and add it all up across the entire sample. This is what we call the total sums of squares. And basically what it represents is essentially a worst case scenario of how good you could do in predicting what y is. Use the sample mean. So in other words, like with respect to the college and high school GPA example, is we're using the sample mean of the college GPAs to predict everyone's corresponding college GPA. And as you can imagine, it's probably not going to do that good of a job. Okay, so again, this is like a worst case scenario, a measurement of how good this predictor y bar is in predicting what y is. But now let's say that we do have knowledge about x, and we want to use x to predict what y is. Well, in that particular case, of course, we would use our sample regression model. Y hat is equal to beta hat 0 plus beta hat 1 times x. So as a measure of how good now our model does in predicting what y is, what we can do, once again, is take all the observed y's, subtract off the corresponding predicted values, square that, and sum. In other words, take the sum over I equal 1 to n of y sub I minus y hat sub I squared. This is what we call our sum of square errors, or SSE. And so now as a measurement of improvement then, of now when we take into account x, like for example high school GPA to predict college GPA, as a measurement of how much we've improved, what we can do is take a look at the total sums of squares minus the sum of squares for error, and this is our measurement of overall improvement. As a way to express then this numerical quantity in a nice form, we're going to express it now as a percentage. So what we're going to do is look at total sums of squares minus the sum of squared errors divided by the total sums of squares. In other words, what is the percentage reduction in the total sums of squares when we now use x to help predict y? And so this is what our expression then looks like. And this is what we call our coefficient of determination, or R squared. So, for example, let's do a simple numerical example here. Suppose the total sums of squares is 10, and the SSE is 9. So you can see by using x in this particular case, you're not really reducing the overall prediction error by using x. So the R squared in this particular case would be 10 minus 9 over 10, or in other words, 1/10, or 0.1. So in other words, you've only gained about 10% from using x to predict y rather than just simply using y bar. Not much of an improvement at all. But now let's change things. Instead of SSE being 9, how about SSE is now 1? And you can see, just comparing 10 to 1, that's a dramatic reduction. Well, how much of a reduction? Well, it's a 90% reduction, 0.9. And so in that particular case, yeah, a lot has been gained by using X to predict Y rather than simply using Y bar itself. And so that's how we can then interpret what this R squared is measuring. It's the amount of reduction in the total sums of squares, or the amount of reduction in terms of your overall prediction error by using X to predict what Y is. So this is a percentage. It's between 0 and 1. Here's a formal interpretation. Suppose R squared was 0.9 when I go over this interpretation. 90% of the variation Y can be explained by using X to predict Y. Thus, the error in predicting Y can be reduced by 90% when the regression model is used instead of just simply Y bar. That's if R squared was 0.9. Note that this capital R with a little 2 in the superscript. The capital R part is not meant to represent necessarily a random variable. It just so happens for some reason, people typically refer to this quantity as R squared always, rather than call it its official name, coefficient of determination. The square there, why do we have that? One way you can think of it is notice how we have these squares there. But in the next set of, later in this set of notes, I think you'll see too why we ended up calling it R squared. There's some additional information that will be presented. So again, R squared then is a measurement of fit for the regression model. How well does this model fit your data? How close essentially then are the points to the line? So you can think of it this way. The farther the points are from the line, the lower the R squared will be. The closer your points are on a scatter plot to the actual regression line, the larger your R squared will be. And so here's just a simple numerical scale to essentially illustrate that. Okay, so let's go back to our sales and advertising example once again. This is on page 3. So we've already found total sums of squares. It was 6. And you can see when we use X, when we use advertising to help predict sales, it dramatically reduces our error down to 1.1. So my R squared ends up being 0.8167. In other words, about 82% of the variation sales can be now explained by using advertising to help predict that sales. So, or you could also say 82% of the variation in sales is due to advertising. Okay, that seems pretty good. And, why did we have such a large value there? Well, take a look at the scatter plot. Look how close those points are to the line. Now, with respect to the college and high school GPA example, we've already estimated this model before. We put the results into mod.fit. We've looked at the summary of mod.fit before, and here's the corresponding output. The reason why I have it here is I want to show you in the output where this R squared is located, 0.5768. And so what this means in terms of this problem is that about 58% of the variation in college GPA can now be explained by using high school GPA to predict it. So again, that's really a significant amount. So that what that again says is that if I know your high school GPA, I essentially know 58% of how much those college GPAs will be bouncing around. In other words, the variability. I can explain 58% of it by just knowing the high school GPA alone. So overall, the model seems to fit decent. I'm sure we would like to have higher. And we'll look at another subsequent subsection where what happens if we maybe incorporate other variables into the model. One could also use R squared for that to measure not just one variable, but maybe 5 variables or even more variables to see how well we can predict what Y is rather than just simply using the sample mean of the Ys. So here's a plot that helps demonstrate what's going on. So high school GPA, college GPA. Here's the sample mean. If I didn't know anything at all about X, That's what I would use. I would use my sample mean to predict what y is. And if we look at this particular observation right there, which I believe, did I write that down? Yep. So this is observation 18 in my data set. And we can see, if I wanted to predict that by y bar, the sample mean, you can see how far we would be off, about by about 1. But if instead I use y hat to predict what y is, we can take into account what x is, you can see how much dramatically my error has been actually reduced. That's why we can say, yeah, 58% of the variation in y, in terms of how these points are bouncing around here, can be explained by knowing what x is, or high school GPA is. Well, what about this college GPA example regarding the number of times one eats pizza? We've seen before that the p-value for that particular inference that we made was quite large, meaning that there wasn't sufficient evidence to indicate a linear relationship between pizza and college GPA. And so because of that, you would probably expect that indeed that this corresponding R-squared would be low. And in fact, it is. Thus, only about 1.2% of the variation in college GPA can actually be explained by the number of times a student eats pizza. And if we take a look at the plot again, we can see the points are kind of a random scattering. They're not close to the line at all in comparison to what we had with the high school GPA plot. Okay, so that's the coefficient of determination. Excuse me. Now there's another numerical summary measure that's closely related to it. And this is called the correlation coefficient. Some people will call it the coefficient of correlation, the Pearson correlation coefficient, or it's just simply correlation. This value is very closely related to the coefficient determination, capital R squared. However, with this particular this numerical measure that we're going to look at, you actually don't need to do regression at all with it. So you might be wondering, why are we looking at it in this section then if we're not doing regression? The reason is because it's close relationship to the coefficient of determination. Okay, so the correlation coefficient is a statistic. Here's how we can calculate the observed value of the statistic. We're going to call it a lowercase r. Again, you might be wondering, okay, why am I keep on using this letter r here? You'll see why shortly. And the way that we calculate is we simply take the sum over an entire data set, all my x's, subtract off x bar, times all the y's, subtract off y bar. Again, sum it. And then take it divided by the square root of the sum of all the xi minus x bar squares, and times then the square root of all the y minus y bar squares sum. That's what this numerical measure is. And in the end, this numerical measure is always between -1 to +1. The closer you get to +1, the stronger the relationship between x and y. But because it's positive, though, that gives you actually another bit of information. The closer you are to +1, the stronger the what's called a positive relationship exists between x and y, meaning as x goes up, y goes up. Okay? Let me erase that. Now, the closer you are to -1, then the stronger the relationship is between x and y, but now the stronger the negative relationship. In other words, what that means is x goes up, y goes down, as what I just illustrated there. Then the closer you are to 0, the less there is a relationship. So at 0 itself, if you did a scatter plot of all the points, sorry, I didn't say that this is what I was doing before. The closer you are to 0, the more of a random scattering of the points, meaning the less of a relationship between x and y. At exactly equals 0, essentially there's no relationship. Okay. Now, it just so happens, if I were to take the square of r, I get the coefficient determination. So that's why I'm continuing to use r here. It is kind of strange, though, why I have a capital R for r squared, where I wasn't necessarily talking about necessarily a random variable there. Here I have a lowercase r where I'm talking about an observed value. Don't blame me. Blame the people who came up with this notation a long time ago. I decided to use what's the most common notation. So sorry if there's confusion, but if there is, please make sure you ask. Okay. So what are the advantages of using just little r itself instead of r squared? Well, no regression models needed. And then we also have information about the direction, you could say, of the association. Is it a positive? Is it a negative type of association? Okay. So a long time ago, when I first started teaching this, I had a particular textbook for introductory statistics, and here's a scan-in image from this textbook, which really demonstrates what's going on. And I kind of did this with my own drawing. And so if little r here was negative 0.99, we can see how the points are going downward as a function of x. So as x goes up, y goes down. So we have essentially, if we did have a regression model here, would be a negative slope. We see how the points are tightly clustered. And if r was negative 0.75, now you can see the points are getting a little bit further away from each other, not as tightly clustered as before. If r is equal to 0, we have no trend at all in that plot. When r is positive 0.75, you can see this upward trend that goes up. And as r increases, then the points get closer and closer together. Okay. Now let's talk about inference now with respect to this correlation coefficient. Very often you will see people define now the correlation in the population itself by a numerical summary measure, a parameter called rho, R-H-O. This is the Greek letter rho, not a P. It's the Greek letter rho. And the purpose is to measure the relationship between x and y, not necessarily with a regression model. This rho has the same numerical scale as what we just got done seeing with r itself. Okay? And so similarly to what we've done before, we're going to take what we have from our sample. We're going to try to make inferences back to the population for what rho is. And if we let capital R now be an actual random variable version of this lowercase r, what one can show is that if you take capital R times the square root of n minus 2 over 1 minus r squared, this has a t-distribution with degrees of freedom n minus 2. Don't worry about mathematically deriving it. Take my word for it that this does have this t-distribution. Because I have that distribution, that means then I can find corresponding quantiles from my t-distribution. Find these quantiles in a way so that if I put an inequality inside of a probability statement, I can then say this probability is equal to 1 minus alpha. That then leads us to ways to do inference. So let's talk about a test statistic method for a hypothesis test. State your hypotheses. If rho is equal to 0, that's going to be our HO. There's no linear relationship between x and y. If rho does not equal 0, there is a linear relationship. We calculate our test statistic using information that's observed from our sample. We state critical values. We decide if we reject or don't reject HO, just like what we would in any two-tailed test situation. And then state our conclusion in terms of the problem. Reject HO, yes, x is linearly related to y. Don't reject HO, well, there isn't sufficient evidence to show that x is linearly related to y. To do the p-value method, we do what you would normally expect. Here's my p-value. Capital T is a random variable t from the corresponding t-distribution. We look at the probability that that random variable is greater than the absolute value of the test statistic take it times 2 because we have a two-tailed test. If the p-value is small, you reject. If the p-value is large, you don't reject. Now, what's interesting is, despite us not doing an actual regression model, is that this hypothesis test here is exactly equivalent to doing the hypothesis test for beta 1 is equal to 0. And hopefully that makes some intuitive sense why that would occur. Because when we had our regression model, in terms of the population regression model, we see if beta 1 is equal to 0, what we would expect y to be on average is not going to change as a function of x. So it makes some intuitive sense for that to occur. Now, in terms of a confidence interval, in terms of doing a good confidence interval, there's a number of different confidence interval procedures out there. We're going to talk about one that uses what's called Fisher's transformation. And here's the setup. If I were to take the square root of n minus 3 times 1/2 times the natural log of 1 plus r over 1 minus r, subtract off the same quantity but now written in terms of rho instead of r, this quantity can be well approximated by a normal distribution, standard normal distribution, for a large sample. So because of that, then, if we wanted to, we could take what's in the middle here and find a corresponding confidence interval for it using methods that we've kind of done before, where we have an estimator, we have a quantile from the standard normal, but now we also have this weird term here, 1 over the square root of n minus 3. That's my left side. The right side of my confidence interval is exactly the same, but now I have a plus there instead. Now, what one could do, because in the end we want an actual confidence interval for rho. We don't care about this transformation. This transformation just helps make this standard normal distribution work out well. So how about we call this left side L for lower bound? How about we call the right side U for upper bound? And then we try to solve for rho. And you could do some algebra to do that. And this is what you would get. So that now my confidence interval for rho is as follows. I use the exponential function of 2 times L, that lower bound, minus 1. Then take e raised to the 2 times L plus 1. That's my lower bound. My upper bound is exactly the same, but now I replace the L with a U. That's my confidence interval. Okay, so let's go back to the college and high school GPA example again. How can I find the correlation coefficient? Well, simply, there's a function R called core. So for the X argument, I put in my high school GPAs. For the Y argument, I put my college GPAs, and there is my R, 0.76 about. Notice how it's positive. And from what we saw in the scatter plot, yeah, it looked like there was a positive relationship, meaning as high school GPA goes up, college GPA goes up. Also notice it's kind of close to 1. And from what we saw in the scatter plot, we saw those points are somewhat close together in that scatter plot. And so that's why we're up to 0.76 for this correlation coefficient. Now, another way you could use core is that for just an X argument, suppose you just put your data frame in there instead. And what R calculates then is essentially the same thing, but it puts it into what's called a correlation matrix, meaning that we have some rows, we have some columns of information there. For those of you who have taken a matrix algebra class, this is indeed a matrix as you would see there. So if I match up high school GPA with college GPA, there is my R again. If I were to match up high school GPA and high school GPA in terms of what's the correlation between the exact same variable, well, it's exactly equal to 1. Think of plotting high school GPA on the x-axis, high school GPA on the y-axis. You would have all the points going on a straight line there. Correlation would be 1. Okay, so now let's do a hypothesis test. Is there a linear relationship between high school and college GPA and the population? We're going to use alpha 0.05. To do this test really easily, there's a function R called core.test. X argument, high school GPA. Y argument, college GPA. We're going to do a two-sided test here. Method. Okay, you might remember me mentioning a few minutes ago that some people will call the correlation coefficient the Pearson correlation. That's why we use the word Pearson there. There are actually other measures of correlation, which we won't talk about in this particular class. And so that's why we have to specifically indicate which measure we're talking about. Definitely the Pearson correlation measure is the one that's used most predominantly. Let's say I want to use a confidence level of 0.95 to find a confidence interval. Okay, so my t-test statistics, 4.95. My p-value is very small, 0.001. And in fact, you should compare this to when we were doing a hypothesis test of beta 1 is equal to 0 versus beta 1 does not equal 0. This is exactly the same test statistic, exactly the same p-value. The corresponding confidence interval says 0.48 is less than rho is less than about 0.90 with 95% confidence. So we can go through the formal test here. I'll let you go through that. And also notice here's what R is as well. And we end up rejecting HL here. So there is a linear relationship between high school and college GPA. If you wanted to, you could also look at this correlation coefficient there. So this is on page 16. Let me just get there real fast. Take 0.7595 squared, you get our R squared that we saw previously. Also, I go through the details. Please look at this on your own about how one could actually essentially find this confidence interval for the correlation coefficient without the core.test function. Okay, so some final notes here. Suppose you had R equal to negative 0.02. So you might be thinking, oh, there's really no relationship between X and Y. But something that perhaps I didn't emphasize enough is that this R here looks at the linear relationship between X and Y. You could still have some other kind of relationship as what we see here. So we can see this kind of a quadratic relationship. In that particular case, R will be close to 0. But indeed, we do see that there is a relationship there. Also, having what's called strong correlation, meaning you're close to 1, close to -1, does not necessarily imply that, let's say, X causes Y. So a correlation coefficient is not a measure of causation. And you got to be very careful about that. Here's an example that I found in another book a long time ago when I was first starting to teach that I think still holds true here. And please read this on your own. But basically it shows you kind of a nonsense example of where there's a high correlation, in terms of high positive correlation, but one cannot assume that this X here causes its corresponding Y. It doesn't make sense. So please read that on your own. So what we just got done talking about here is essentially two measures, although they're very similar, that allow you to measure the association between X and Y. One thinks about it from a regression model case, another one does not.